yesterday we talked about independent events versus dependent. A card is drawn from a deck and then replaced. So you got the deck of cards. Look at, here's a sample space right in front of you. This is from the handout I gave you yesterday. We got a total of 52 cards. We have, let's see, clubs here, hearts, spades, and diamonds. The four, they call these suits, like a suit. When you put on a suit, in cards is actually the clubs, the hearts, the diamonds, and the spades. Okay, so if I say, what suit are you talking about? I'm asking about this. Okay, these are your suits. All right, here we go. Card is drawn and then replaced. So if I draw a card, look at it, and put it back in the deck, that means the deck, the sample space has not changed the second time I draw a card. Okay? So that means these two events would be independent. The second time I draw a card has no influence, is not influenced by the first time I draw the card, because the sample space is the same cards are there in the deck, and the chances of me getting another card is the same. So this would be an independent event. So notice on that handout I gave you that looks like this. For events that are independent, it's this. The probability of A and B is equal to the probability of A times the probability of B, if it's independent. So me drawing a queen, putting it back in the deck, and then me drawing an ace are totally independent events. That's why I'm going to use this formula. So follow me. Here we go. Let's do this. So let me follow that formula. But now instead of A and B, I'm going to put Q for queen and then A for ace. So I'm going to follow this formula that's on your handout, but instead of A and B, it's just Q and A for ace. So the probability of getting a queen and then an ace is equal to the probability of getting a queen times the probability of getting an ace. Let's just multiply those puppies. Here we go. Let's find the first one then. The probability of getting a queen. Let me circle the queens. Here they are. There's 4 of them. 1 per suit. Thank you, Gallegos. 4 out of 52. There's your probability. Okay, now let's circle the aces. Let's circle those puppies, right, Gallegos? Watch this. There's 4 aces. I'll circle them. Ace of each suit. So let me multiply that by 4 out of 52. Fraction times a fraction, that's middle school stuff. Let's see. Numerator times numerator, that's 16. 52 times 52 is I have no clue. That's what it is. 179. Nah, it's way bigger than that. 52 times 52. 2,704. You actually weren't. It's in the thousands, man. All right, I'm going to change it to a decimal for now. So 16 divided by 2,704. 0.005. So I'm going to round to the nearest hundredth. That's this decimal. So that's 0.001 approximately. It's about a 1% chance of getting a queen, then getting an ace. With replacement. This is called a with replacement. We replaced a card and then got another card. Okay, so that's your warm-up. Question on this one? Absolutely. This is number 2 on our warm-up, our last one. Go ahead and write this one down. Our last example for the day. This is number 2. This one's got an A, B, and C. A bowl contains 3 red balls, 2 blue, and 5 white. A ball is selected without replacement now. Notice that. Without replacement. Think of the one we just did where we replaced the card that we first got, right, Moreno? A second ball is then selected. All right. Here is a case, ladies and gents, of dependent events, the one all the way at the bottom. Again, we're only covering the second, the last one, the third and fourth one. Next week is the first and second. Today is just independent, dependent. This is a dependent event because I'm not replacing the first ball I get, which means the sample space is now reduced. Let's see, a bowl contains 3 red balls, 2 blue, and 5 white. Okay. So 10 of them total. Let's find the probability of selecting 2 blue. Notice how a ball is selected without replacement. This is the key word right here, without replacing it. That gives it away that we're dealing with dependent events. The second ball that I pick is influenced by the first ball I picked because the sample space is now reduced. Let's do it. So we'll do A first. Here we go. Here we go. Here we go. So here's A. Find the probability of selecting 2 blue. Look, I'm going to put B and B is equal to, here we go. I'm going to follow the formula. Remember, the formula really says this: the probability of A and B equals the probability of A times the probability of B given that A happened. Remember that bar from yesterday we talked about? That means given that. I'm using this formula now, but with the 2 blue balls. Is it blue? Oh, yeah, 2 blue balls. Chill. Whoa. That was kind of scary there. Thank you, Gallegos. You're awesome. All right, here we go. So the probability of the first blue one. I know, big time. Head on. So the first blue one, here we go, is, how many are there that are blue? Out of how many? Chill. 3 plus 2 is 5, plus 5 more is 10. Cool. Times, here we go. The second blue one, given that I got the first one. So now there's 1 left. Out of how many now? No, I already got the first one. So 9 left over. So this is the second blue ball, given that I got the first one. So really, I kind of, let me redo this here real quick. Let me bring this down. Let me finish the formula that I never finished, actually. So this should have been this. If I follow the formula, B and B, this should have been probability of the first blue ball times the probability of the second one. Look, I'll put B sub 2, given that I got the first one. Look at, that's the way it should have looked. I forgot to write the rest there. So the probability to gain 1 blue ball times the probability to gain the second one, given I have the first one in my hand. So the 1 out of 9 refers to this probability. The 2 out of 10 refers to the first one. Right, Gallegos? You're showing me you can't handle there. So I have the floor. You shouldn't be writing on her book. Just to let you know. Little FYI. What's up, Boleto? Here we go. Thank you. Let's multiply these puppies. We have, see, numerator times numerator is 2 over 90. Let me make that into a decimal. 2 divided by 90. 0.02. So that's part A. I rounded the nearest hundredth there, right? questions for part A? Sure. Go ahead. So B is find the probability of a blue, then a white. Here we go. A blue, then a white. So this is part B now. The probability of getting a blue ball and then a white. Since they're dependent on not replacing the ball, here's a formula. The probability of a blue times the probability of a white, given that I got the blue first. Look at that. I'm just following this last formula, the dependent events formula. Let's do it. The probability of getting a blue is 2 out of 10. We know that. There's 2 of them. The probability of getting a white, given that I got the blue. How many whites are left over if I got a blue first? There's 5 whites still, huh? Because I didn't get the white first. So I got 5 whites, but how many balls are left over? 9. That's why it's dependent. This is the white, given that I got the blue, right, Hernandez? Stay with me. Let's do it. Let's multiply this puppy. Beautiful. Close. Nice. Nice. That's going to be 1 out of 9 times, which is really 1 divided by 9. 11%. There's an 11% chance you get this. 0.11. 11% chance that happens. You get a blue, then you get a white without replacement. Questions? Last but not least, here we go. Go ahead. Let's do it. C. Not bro, it's Miss Mungia. Thank you. Awesome. Mungia. Find the probability of getting a red and then a blue. Here we go. Look at this guy. Times times the blue given I got the red. So it's a red, then a blue. That means this one's the R. Yeah. First getting the red, not replacing it, keeping it, then putting your hand back in the bowl, getting a blue, given you got the red first. Here we go. The probability of red will be, let's see how many reds are there. See, 3. It's 3 out of 10. Blue is 2 out of 10, but now there's 9 balls because we got 1. Multiplication time, we're good to go. 3 times 2 is 6. 10 times 9 is 90. 6 divided by 90, let me round to the nearest tenth, let's do, or hundredth rather. 6 divided by 90, 0.07, so a 7% chance of that happening. Unlikely, but possible. 7%, 11%, 2%, depending on the situation. All right. This.